So a second look at an example of being able to use the total differential to approximate displacement. We have this function x ln 2x plus 3y, and remember that we're trying to approximate, by using the total differential, the change in x and y, and x was going to change, remember, from 1 to 1.02, and this is from the original problem. And remember, y was going to change from 2 to 1.99. Alright, so we have to find the derivative, and then we have to find the total differential. Oh, and by the way, we found earlier that dx was the difference between those, so that's 0.02 terminal minus initial. And then remember, we found dy to be negative 0.01. Alright, so we're going to hold on to those because we need those values a little bit later when we find that total differential. Right, so fx is going to be a product rule. Right, so notice that we have a function of x here, and we have another function of x contained inside the natural log. Our product rule, remember, fg prime plus f prime g, or the commutative property of that. It doesn't really matter. So I'm going to take the derivative of x, which is 1, times the natural log of 2x plus 3y. And to that we're going to add x times the derivative with respect to x, so that's 1 over 2x plus 3y, times 2 from our chain rule inside of that 2x plus 3y. Or another way to write this, natural log 2x plus 3y plus 2x over 2x plus 3y. Right. Now we need fy. Fy is going to be equal to the derivative with respect to y. So remember, we still have that x, okay, from up here, from the natural log. This is just a constant, like a 5 or a 10 or something like that with this x, so we're not worried about it. Natural log is going to become 1 over 2x plus 3y, and then finally we're going to multiply that by the derivative of 2x plus 3y with respect to y. Or another way to write that, 3x over 2x plus 3y. Right. And now what we're going to do is we're going to get dz, the total differential. The total differential is going to be what we got for fx times dx, so that's natural log of 2x plus 3y plus 2x over 2x plus 3y times dx. And to that we're going to add 3x over 2x plus 3y dy. All right, so that's our total differential. We're going to hold on to this because that's going to approximate the displacement. All right, so now let's approximate dz. All right, so dz, now remember, we have our initial value of 1, 2 for xy, and then dx is 0.02 and dy is 0.01 negative. So dz is going to be equal to natural log 2 times 1 plus 3 times 2 plus 2 times 1, 2 times 1 plus 3 times 2, and we're going to multiply all of that by 0.02. From that we're going to subtract 3 times 1 all over 2 times 1 plus 3 times 2 times dy, which is negative 0.01. All right, this should be add. Now let's approximate dz. I'm just going to do that in my calculator. So we get ln of 8 plus 2 over 8, and we're going to multiply that by 0.02, so that becomes 0.04658, and to that we're going to add 3/8 times negative 0.01. Alright, so I end up with 0.04283 39. Alright, so I'm just going to hold on to this value, which is our dz. Alright, now, let's try to figure out what delta z is. Alright. Remember our original function, x ln of 2x plus 3y. And so we're going to substitute the terminal point. Remember our terminal point is 1.02. So we're going to have 1.02 ln of 2 times 1.02. And our terminal y was 1.99. And from that we're going to subtract when x is 1. That's 2 times 1. And y is 2. All right, so I'm going to shove this into my calculator. See what we get out of this. So we have 1.02 times the natural log of 2 times 1.02 plus 3 times 1.99. And we're going to subtract the natural log of 8 from that. Alright, and I get 0.042863. Alright, so I'm not too good with numbers, but I noticed that the first 4 digits, 0428, are accurate. Alright, so now technically I guess right here it stops being accurate because if you round the 6, the 8 actually rounds up to a 9. Alright, so we're at least accurate to the thousandths place. Alright, because there's nothing else that can suggest that we're not. Alright, so if I was to compare these, we would say that dz is accurate when used to approximate delta z to the thousandths place. Alright, and that's a good thing because the more accuracy, the more reliable we have to be able to work with something. Alright, so that's another application of our total differential, is being able to use our total differential to approximate displacement. Let's take a look at just a couple other applications. So we have a length of and width of a rectangular fence, and they're stated to be 30 meters and 24 meters respectively. And the company that we're looking at, installing the fence, wants to allot no more than 1 meter of error for both each the length and the width. What's the maximum error that could occur from the area enclosed by the fence? Alright, so to be able to do this, it's pretty easy. We can start with our formula. Area equals length times width. Alright. And what we can do is we can just go ahead and find the total differential for this. Now notice that we have two variables, L and W. So I'm going to say the total differential dA. The derivative of L is 1, but then we have derivative L, dL, the change in L, plus the derivative of W is 1. So we have L times 1 dW. Or in other words, dA is going to be equal to W dL plus L dW. Notice that the length is 30, the width is 24. And the question is, what is dL and what is dW? Well, dL and dW are the error. And notice that there can be no more than 1 meter of error in each the length and the width. All right, so dL is going to be equal to dW, which in this case is going to be 0.1 meter. And we're just going to substitute everything back in to find the maximum error that could be allowed. Right? And so, remember we said that W was 24. So we have 24 times dL, which is 0.0 or 0.1. And these are meters and meters. Plus L, which is 30. Times dW, so 30 meters times 0.1 meter, and that's 2.4 plus 3, and that should work out to be 5.4 meters squared. All right, which doesn't seem like a lot. However, if we approximate that, remember, a meter is roughly 3 feet. It's a little bit more than 3 feet. It's 39.36 inches or something like that. But roughly what we have is 5.4 times 3. So we have roughly, oh boy, a pretty good amount. All right, so we're probably going to have, oh boy, a pretty big area. So that's a lot of area to have an error with, especially if you're the person that's purchasing the fence. So that's probably why you want to not have that much error, because you're just going to be spending a lot more money. One final example is sensitivity analysis. So we have a cylindrical steel storage tank. Is built to be built. It's going to be 10 feet tall and 4 feet across in diameter. And we know that steel expands and contracts as temperature changes. And the question is, which one will affect, or which one has more effect over the volume? In other words, is the diameter more sensitive or is the height more sensitive? All right, so one thing that we have to remember is the formula for volume. All right, so we're looking for the volume of a cylindrical tank. Right, that's pretty easy, right? So we have our cylindrical tank, and we remember that we have pi r squared, and we have a bunch of pi r squareds times the height. All right, so it's almost like that cylindrical, or that disc and washer method that we saw in Calc 2, except we're just kind of throwing it together. So the volume is going to be equal to pi r squared, which is the area of each of the circles, times the height. And if we want to find the total differential for this, dV is going to be equal to 2 pi r h dr. And then if we want to take the derivative with respect to h, all right, since we have a product rule going on here, that's going to be pi r squared times h, which is going to be 1, or derivative of h, and that's going to be dh. All right. Now, of course, what we know is we know that the tank H is 4 feet tall, and the diameter is 4, which implies that the radius is 2. So we could substitute those right away into dV. So dV is going to be equal to 2 times pi times 2 times 4, or times 10, excuse me, dr. Right? It doesn't say anything about what dr and dh are, but that's okay. And then pi times 2 squared dh. And if we simplify this, dV is going to be equal to 40 pi dr plus 4 pi dh. All right. And then the question is, how does this help us to answer the question? So, of course, the question is the overall volume of the tank more sensitive to changes in diameter or in the height of the tank? And in fact, if you look at the coefficients, we have 40 and 4 pi. This is the change in the radius. All right, so we have 40 pi times the change in the radius, or 4 pi times the change in the height. All right, so in fact, what we can say is that there's a factor of 10 for the radius sensitivity, all right, compared to the sensitivity of the change in the height. All right, so we can clearly say that since the coefficient of dr is greater than the coefficient of dh, okay, what we can say is that the radius, okay, is, I guess, has more influence over the volume of the tank. And what that means is that the volume is more sensitive to changes in the radius. So the volume is more sensitive to changes in the radius, and hence the diameter as well. All right, and even if we were to divide that by 2, it would be 20 pi compared to 4 pi, which is certainly much larger. All right, so that's a way that we can kind of utilize the differential to be able to analyze sensitivity in changes. All right, it's actually one of the more important types of applications to this. So hopefully it's a good overview as to what the total differential is, and then also an overview as to how to utilize the total differential in applications.